Hey guys, how's it going? All right, so today is Wednesday, November the 4th. It's an A day. This is day 9 of the second quarter. I hope you guys had a wonderful election day off. I'm interested to see how that goes and see who wins and everything. So that'll be interesting. I've certainly enjoyed the day off. I did go vote, so I took the time to go do that. I also was able to go with my wife to her doctor's appointment and do a sonogram with the baby and here's heartbeat and all that kind of stuff. So that's good. We are expecting the baby next week or maybe more likely the following week. All right, so it could be next week, but probably the following week, so about 2 weeks. And so when the baby does get here, we will probably be in the hospital for a couple of days, anywhere from a couple of days to a week. And so we'll be in the hospital for that time. And so I'll have stuff posted for you guys to do each day. But I won't be doing much because I'll be in the hospital with her, preoccupied. So there'll be some easy days for you guys. And then the following week after that, once we get home, I will still be out sick for a week to help with the baby and to kind of bond with the new child, our new child, and I'll be getting online and doing some videos like I'm doing right now, doing videos and doing some lessons. I just won't be in the classroom, all right, but I'll still be making videos and posting stuff online. And I'll try to get on to the Google Meets during class time in order to at least post those videos and give you guys those things, okay? So today we're going to do a warm-up atomic structure DOL, which is demonstration of learning. So each student will be assigned a different element. And I see a typo there, so I got to fix that. Students are to demonstrate their learning of concepts in Unit 3. Students must complete the activity for credit. All right, then we're going to do an Ed puzzle where you go through this video and answer questions. The Ed puzzle video will start here and go all the way through our notes, but the questions in the Ed puzzle will just focus on the notes. And I'll try to keep the Ed puzzle as short as I can because I know we're getting super tired of them, but it's just the best way to teach the concepts and to ask some questions to make sure that you guys are thinking about what I'm talking about. Okay, you guys need to complete the Ed puzzle by Friday. Okay, not next Friday, but Friday. So let me fix some of this stuff here. So this should be A, and then this should be by this Friday. There we go. Save. Okay. And then we're going to have an exit ticket at the end of class that students need to be complete for credit. And this exit ticket just asks, what did we learn about today? And then maybe some questions about electron structure. Okay. Give you a chance to practice and see if you're understanding what we're talking about. Okay. And if you're not understanding yet, that's fine, but it's a check to kind of see where you guys are at and make you think about it. Okay. So let's start with the warm up. I'm going to say that I'm going to pick a random atom. Let me look on the periodic table here and see who I want to be. I'm going to pretend like I'm an atom or an element. So let's see. One of my favorite elements is platinum. So where is platinum? Here it is. Platinum is element 78, platinum PT. So I'm going to be platinum. All right, and I'm going to answer the warm-up questions based off of platinum. So let me open the warm-up questions here, and I'll have those ready to go. So let's write some information about what I've got. I'm going to be platinum, element PT. What was it, 78? 78. Platinum. Make sure I spell it right. Platinum. Number 78. Come on now. Why are you not working? 78. Maybe it doesn't work over there. Okay. So there's the information on our element. Erase this. Okay. So platinum has element 78. So let me open up the DOL. And so we're going to put our first and last name in it. So I would type my first and last name on the Google form. And then I would click my class period. Today it'll be 1A or 4A. If you're B, then it'll be 1B, 3B, or 4B. So click your class, and then it says assigned element. So if I'm assigned platinum, why is this not working sometimes? There we go. If I'm assigned platinum, then that's what I'm going to write there. Assigned element is the element that you're assigned. Let me pull up the document that you're going to see when we do this. Okay, let me pull this up. So this is what it's going to look like. And if you're watching this video and you were absent, you need to find your name here and look at your element. So if I am, who should I pick on? If I am Harold, here's my name, here's my element. So Harold would be element aluminum. There's the atomic number of the element. That way you can find it on the periodic table and aluminum. So now I can look on my periodic table. I can look, here's number 1 at the top, and it goes in order of atomic numbers. So 13 is right here, so aluminum. So first you got to find your element on here, which can be a little annoying, especially if you don't know where it's at. It might be, it might take a minute to find it. But I did give you the atomic number, so that does help. It's really difficult to find the element if you don't have the atomic number, right? Like if I asked you guys to find thorium on here, I mean, it's going to take a while, right? There's 118 of these guys here. Okay. So we'll look on here and find our element, okay? Once you know your element, we're on the question here that says assigned element, this one. We're going to type platinum. Okay, what is the atomic number of your element? Well, if I go back to my presentation, it's element 78. Okay, and if you go back to the thing here, atomic number is right here. So if I was Harold, I would be element number 13. That's my atomic number. Excuse me. So my atomic number is 78. And where did my Google form go? All right, Mr. Google form, come back. There we go. So I would put 13 there, okay? This is provided in the table shown during class, so it's from the table. So that's a number that I'm giving you to start. So what I'm giving you to start is the name of the element, the symbol for the element, and the atomic number, okay? And so you can put the symbol there if you want. You don't have to. I'm putting it there because I want to. How many protons does an atom of your element have? So if I had an atom of platinum, how many protons would it have? It's equal to the atomic number. Well, I have the atomic number, so it's the same thing. Oh, platinum is 78. Why am I putting 13? That was for that other element, aluminum. So if my atomic number is 78, I would have 78 protons. Okay, assuming a neutral atom, how many electrons does your element have? Okay, so that means that the protons is equal to electrons. Well, I have 78 electrons, and I have 78 protons. So if I have to equal electrons, then there must be 78 electrons. They have to be equal. It's a tug of war. So if they're neutral, you have the same on both sides. Think about a scale. Think about balancing two objects. Right? If you're going to balance it, you got to have the same size apple on both sides. Same value on both sides for the weight. So 78 protons, 78 electrons. Okay. If your atom gains an electron, what is the charge? So I have 78 protons, 78 electrons. Protons are positive, electrons are negative. So if I gain an electron, that means now I have 79 electrons. So let's think about this. 78 protons, 79 electrons. So I have 78. So my total positive is plus 78. My total minus is minus 79. So what will happen is 78 protons will cancel with 78 electrons. So those will cancel out. And so everything except one electron will be still remaining, right? If I had 78 protons, so think about tug of war. If I had 78 protons over here and 78 electrons here, wouldn't they cancel each other out? So 78 protons will cancel with 78 electrons, but we have 79 electrons. So we have one left over. So that means that the electrons will win. There's one more electron. These are canceled out, right? The 78 protons are equal in strength to the 78 electrons, so nobody wins, right? But if we have one more electron that's added to this atom, well, then the electrons will win. So our charge is -1. We have one more electron than protons, and so it's a -1 charge. Okay, and this will take more time to practice, and it'll make more sense as we go along, but I'm trying to introduce charge balance and figuring out, all this stuff with ions. So if you have a charged atom, it is called an ion. Okay, I-O-N. Okay. All right, Mr. Google Form. So if an atom gains an electron, what's its charge? It's now negatively charged because electrons are negative and you gained one. An atom with the charge is called an ion. Okay, what is the average atomic mass of your element? All right, well, let's look at our periodic table. I'm right here, and that's my average atomic mass. It is beneath the symbol, and I will certainly share this periodic table with you guys during class. So 195.085. I wonder if I could copy that. Control C. Let's go to my Google form. I doubt it'll copy, but I'm going to try it. What is the average atomic mass of your element? Look, it copied. You can actually copy from that. That's cool. I don't know if you guys will be able to do that, though. I think it depends on your software. I'm using Adobe Acrobat Reader DC, and you can actually copy text, which is really cool. That's why I like this program. But if you don't have this one, then I don't know if you'll be able to copy. If not, just look at the number and then put it in the Google form. So there's my number, and the unit for that is either AMU or grams. I'm going to put AMU for atomic mass unit. All right, what is the average atomic mass of your element rounded to a whole number? All right, I have 195.085. So let's go back. Let's clear everything here. 195.085. If I'm going to round that to a whole number, this is the whole number here on this side of the decimal, right? So in this box is a whole number. I have 195. Then I have this decimal. So what you guys are going to do is we're going to look at the tenths place, that next digit. If it's greater than 5, then you're going to round the whole number up. If it's less than 5, then you'll round down. Mine is less than 5 because it's a 0. So I'm going to round down, meaning that I'm going to get rid of the rest of this, and my number will be rounded to 195. Okay, when I say round down, it means that we are getting rid of these decimals and keeping the number that is already there. It doesn't mean I drop this to 194. Okay, and that's a common mistake. So when I say round down, it means I'm keeping this number. Now, if I had 195.5 and I rounded that to a whole number, well, here's my whole number in the box. There's my decimal. We're going to see that number, say, oh, it's a 5. It rounds up. That means that this goes up. And so we're going to round that to 196. So you either round down and keep the 195, or you round up. But you can't get 194. Okay? So if it's above 5, you round up. If it's below 5, you round down. So I'm going to put 195. That is this number rounded to a whole number. 195. Where are you at? 195. Okay. The rounded whole number from the previous question, question number 8, the one we just did, this is the most common isotope or version of your element. Okay. So the most abundant, most common isotope of platinum is platinum 195. This whole number is the mass number. So 195 is my mass number. What is the isotopic notation for this isotope? For example, hydrogen with a mass number of 1 would be hydrogen-1 or H1. All right, so what are we going to do here? So we decided that our rounded whole number is 195. Okay. So 195 is my mass number. And my element is platinum. So what I'm going to do is I'm going to write platinum. Write the name of your element, a dash, and then write that mass number. I know this question seems confusing. That's all you got to do. Write the name of your element, a dash, and then that mass number, that whole number that you rounded. Or I can put PT-195. Either of these is okay. This is isotopic notation. This is the name of the element or the symbol for the element. And this is the mass number. Okay, that's it. So platinum 195 is what I would put there. So platinum 195 or PT-10195. Okay, using the mass number from the previous question, how many neutrons are in my element? Number of neutrons is equal to mass number minus atomic number. All right, I've got a mass number of 195, so I've got platinum 195. I know that my atomic number is 78. Let me double check that. 78, okay. And then my mass number is 195. So I need to subtract these. 195 minus 78. How many neutrons? 195 minus 78. 117. I got 117 neutrons. Take your mass number, 195, minus your atomic number. And remember, if I wrote the symbol like this, PT, and I wrote 195 up here, and then 78 here, remember what I'm going to do is I'm going to take this number minus this number, 117, right? So just keep that in mind. If you're given a nuclear symbol like this is nuclear symbol or nuclear notation. This is mass number. This is the atomic number. Okay. So if you take this one minus this one, you get neutrons. Okay. So I have 117 neutrons in this nucleus of this platinum atom, which again is one of my favorite elements. I don't know why. Okay. Using the mass number from the periodic thing, how many neutrons? 117. All right. Last question. A version of your atom with a different number of neutrons is called an isotope. Iso means same, meaning that it's the same element. So if we think about platinum, if I look up platinum on the periodic table or on Google, platinum isotopes, I'm gonna see what I see. Look what I see, guys. Platinum 195, platinum 190, 192, 196. These are all versions of platinum. They have the same number of protons. They're still platinum. They have 78 protons. But look, their mass numbers are different. And which one is the most abundant? Most abundant platinum isotope, platinum 194. Okay. 33%. There's 6 naturally occurring isotopes. The one is from platinum 194. Okay. All right. So yeah, these are different versions of platinum. All right, so we hit submit. We're good. Okay, now you guys, please listen what I'm going to say. You cannot do platinum. You each are assigned your own element, and I need you to do your element to demonstrate that you understand where we're getting these numbers and what we're doing. Okay, so apply what you're seeing, what you're learning, what I just did to your own element. Use the periodic table. Use the same tools I just talked about. All right. All right, now I'm going to quickly go through the historical development of the atom, okay? So students will be able to understand the historical development of the atom, demonstrate their learning and understanding of atomic structure concepts, and then we're going to talk a little bit about describing the location of electrons in shells around an atom. So I want to start introducing the concept of how the electrons are organized in shells around the atom, okay? All right, so we talked about Democritus. Democritus and Leucippus were Greek philosophers. They were not scientists, so I should cross that out. But they had an idea, and their idea was that all matter is made out of tiny, indestructible, or indivisible units called atoms, or atomos, which is the word, the Greek word where atom comes from. A lot of our words come from Latin and Greek because they were the first large civilizations. Okay, these guys were philosophers. They had ideas on atoms, but they could not prove their ideas. Okay, they weren't scientists. They couldn't test them in an experiment. Now, John Dalton was the first to come up with an atomic theory around the early 1900s. This is his model of the atom. We can call it the Dalton model. We can call it the billiard ball model. That's kind of the two things that it's usually called. He was actually mainly a meteorologist. He studied weather. which is kind of cool. So he said a couple of things. Matter is made out of very small particles called atoms. Atoms cannot be divided, created, or destroyed. Atoms of one kind of an element are identical to other atoms of the same element. Atoms of different elements are unlike. Atoms somehow combine in small whole number ratios to form chemical compounds. Okay? So he had the first model of the atom. In chemical reactions, atoms are somehow combined, separated, or rearranged. Okay? J.J. Thomson is our next scientist. He discovered the electron with his famous cathode ray tube experiments. He worked with cathode ray tubes, which are these old school tubes that light up when you put light through them. You put electrons through them and they glow, kind of like the old school TVs that like I used when I was a kid. Not the flat screen; those are different, but the old school TVs with the cathode ray tubes, the big ones, the big TVs. All right, so he wanted to know what the green glow was in these tubes, and so he watched how they attracted to a positive side and repelled the negative side, and so he determined that there's electrons. Okay. Now he didn't determine the charge, but he did discover the electron, and his let's see, this is his experiment, and then his model of the atom is a new model of the atom beyond Dalton. Dalton just said that atoms were indestructible and indivisible. He said that you can't split them. Okay, and there's nothing smaller than an atom. It's the smallest thing of matter. Turns out Thomson's experiment showed that there's these tinier, smaller particles called electrons, and they're sitting in the atom, much like blueberries are stuck in the dough of a blueberry muffin. So this is called the plum pudding model of the atom. Okay. So he said that electrons are like blueberries stuck in a positive. So the whole muffin is positive, and then there's little electrons that are stuck in the muffin, and they're negative. Okay. Plum pudding model of the atom. And I'm guessing plum pudding is kind of like a European or English kind of muffin kind of thing. I've never tried plum pudding. That sounds weird. But that's what they called it. All right. Experiments continue. The next scientist is Ernest Rutherford. He studied experiments with alpha particles. His experiment was called the gold foil experiment, and you need to know that. He shot particles through a gold sheet, and most of the time they went through it, but sometimes they came back and ricocheted. Okay? And so he said, surprise, a statistically large number of the particles get deflected, and they bounced back. So this is as if you had fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. So this blew him away, this discovery. And so he discovered the nucleus, and he discovered the proton. Okay? His model of the atom is called the Rutherford model, or the nuclear model, because it has a nucleus. And he said that the atom is mostly empty space with a dense, small nucleus. The electrons are in orbit around the nucleus. And then remember we talking about all the comparisons of the size. So here's another size comparison. If the period at the end of a sentence in your chemistry book is the nucleus, then your classroom will be the atom, right? So that's pretty cool. Or if the atom is a football stadium, then the nucleus is a marble. Very cool. Ooh, look at him go. Okay. There's a couple problems with Rutherford's model. Why doesn't the atom collapse then? If the atom is mostly empty space, does it contain a vacuum and kind of suck everything in like a black hole? That's what happens in space. And if the electrons orbit the nucleus, does the orbit eventually decay and kind of break down and change shape? Wouldn't a negatively charged electron be attracted to a positively charged nucleus? So here's some questions about Rutherford's model and some problems. And he kind of just said that there's a dense, positively charged nucleus, and then the rest of the atom that was close by was electrons out there somehow. Okay. Turns out there's a little bit more detail than that. And so that detail came from Niels Bohr. Niels Bohr to the rescue. He was a physicist with an interest in spectroscopy. Spectroscopy is the study of how light splits into a different wavelength. So think about taking sunlight and putting it through a prism, and you can make the colors of the rainbow. So he studied how light would break into its different wavelengths. Okay, and we'll talk about this soon. So yeah, light will split into different colors of the rainbow, and each is a different wavelength or a different frequency. Okay, and he studied this, and he determined that each element has its own unique fingerprint, all right, called the bright line spectra. So he just studied how light interacts with atoms and was able to prove that electrons are orbiting the atom much like planets orbit the sun. Okay, I don't know if this thing works here. I can't run it on my computer. It says the plugin's blocked. But the classic model of the atom, let me pull up a picture that we've seen. Here's an example, and this one's okay. So kind of like this. All right, so you've got the nucleus, and then you've got these shells. And so these electrons are stuck in those shells. They're not just out random about around the nucleus. They're stuck in these energy shells. That's what Bohr said. Kind of like planets around the sun, right? Planets that orbit the sun stay in their orbit, right? They stay in their circle. They stay in their lane. Okay. So we call this the planetary model or the solar system model or the Bohr model. So Bohr made the this model, okay? All right, so here's a summary, and this is what you really need to know. So let me go through this real quick. Democritus and Leucippus were Greek philosophers that first proposed the idea of atoms. John Dalton came up with the first scientific model of the atom. We call it the Dalton model or the billiard ball model. J.J. Thomson discovered the electron with his cathode ray tube experiment, and his model of the atom is called the plum pudding model. Ernest Rutherford discovered the nucleus and the proton. He did the gold foil experiment. His model was called the nuclear model or the Rutherford model, named after him. And actually, J.J. Thomson was his teacher, and then Ernest Rutherford was a teacher of another one of these guys, I think Bohr. Niels Bohr came up with the planetary model of the atom, solar system model, or Bohr model, and he discovered that electrons are in orbits. All right, it turns out that a little bit later, so Niels Bohr said that here's the nucleus, and electrons are in these orbits, right? And so this kind of looks like a two-dimensional solar system, right? It turns out electrons can zip around at different angles, right? And so we can kind of see how we can get our picture of our atom. And so we can watch how these electrons zip around the nucleus, and they kind of make a giant cloud. Okay? So you can see how it goes over time, right? And so the electron is just going to make this giant cloud around the nucleus, and we can put a nucleus in here. Here's the nucleus, this tiny thing. All right, and so these electrons zip around however they want. The electrons actually can disappear and reappear, and they're actually hard to follow because of a couple of reasons. So this is called the quantum mechanical model of the atom. Quantum is kind of means small, and it's kind of weird science. It's got weird behavior that doesn't match what we see on our scale as humans. So Schrodinger, Erwin Schrodinger, is kind of the main scientist credited with this, but it's kind of a team effort. A couple other notable contributions for the atomic history is James Chadwick. He discovered the neutron. Robert Millikan discovered the charge of the electron. He determined that it was negative, and then he did the oil drop experiment. All right. Henry Moseley was another one, and he helped organize the periodic table by atomic number and studied the atomic number, determined that protons were positive. Well, him and Rutherford at the same time, several of them determined that the proton was positive. All right, so there's our history in a nutshell. Okay, almost done here, guys. So electron structure. According to the Bohr model, electrons are arranged in shells. Each of these shells is called an energy level. The first shell that is closest to the nucleus can hold up to 2 electrons. Any electrons added after that must go into the next shell. The second shell and every shell thereafter can hold 8 electrons. So it's very important for us to understand, as you build an atom, you start with a nucleus in the middle, and then you've got the first shell. First shell can hold 2 electrons. That's all you can put in there. Okay, and sometimes I think about this shell. Think of it like a bed. Think of it like a small twin bed that you would have if you were like kind of young. You can probably only fit 2 kids in there comfortably, right? I mean, if you put another kid in there, they're going to be touching, they're going to be fighting, kind of fighting for room. If you put 2 in there and they're kind of small kids, that'll be fine. But if you put more than 2, there's not enough room. They're not comfy. And the reason you can only put 2 electrons in this shell is because they repel each other. Okay. All right, so that's our first shell. Let's look at our second shell. Second shell is much more larger, and it can hold up to 8. Okay. So that's all I need you guys to know. First shell of electrons around an atom can hold 2 electrons. Second shell can hold 8. All right, and these shells do have names, and we'll talk about that. And we'll talk a lot more about electron structure. But for now, we just need to know that the first shell can hold 2 electrons. And sometimes we say that this shell is called n equals 1. That just means that the energy level is 1. And we call them energy levels or shells. And so we've got a couple shells. There's 7 shells on the periodic table for all elements. So there's n equals 1 all the way to n equals 7. Okay, and so we can have anywhere from 1 shell all the way to 7 shells. Okay, and so the first shell can hold 2, and then after that it's 8. And that's a simplification, but it works. All right, so I'm trying to make this kind of easy for us. All right, first shell can hold 2. After that it's 8. Okay, so let's draw some electronic structure for some atoms. So let's start with hydrogen. Hydrogen is element 1. It has 1 proton. It has 1 electron. So here's the nucleus of a hydrogen atom. 1 proton in there. And then here's the first shell. And that first shell, let's draw 1 electron in there. And that's it. So n equals 1. And how many electrons can fit in there? 1 electron. All right, so this just means that for a hydrogen atom, if you were to look at it up close, it's got the nucleus, and then it's got 1 shell, and it's got 1 electron in there. And then it's got 1 proton in here. All right, and so equal and opposite charge. 1 proton, 1 electron, they cancel out. Think about a tug of war. 1 positive, 1 negative, they cancel each other out. So that's hydrogen. Now, this first shell can hold up to 2. So if we build helium, helium has 2 protons and 2 electrons. So here's our nucleus. 2 protons, 2 positive in that nucleus. And then here's the first shell. That first shell, n equals 1. That first shell, that's what it's called. N equals 1, first energy level. It can hold 2 electrons, and we're going to put both of those electrons in there. And so we're going to put 1 electron here and 1 electron here. So that just means that we have 2 electrons around that atom. Maybe we could draw it like this. Let me change colors here. I want to show you guys something called the Lewis dot diagram. So here's hydrogen. And if we want to show that there's 1 electron orbiting hydrogen, write the symbol for hydrogen and then put a dot there. That means that there's 1 electron on hydrogen. And let's do the same for helium. 2 electrons. All right, so it's got 2 electrons buzzing around it. All right, let's look at lithium. Lithium has 3 protons, 3 electrons. So let's look at the nucleus. The nucleus would have 3 protons. And we're not worried about neutrons here. There's neutrons in these atoms, but we're not really worried about it. We're just worried about protons and electrons. So there's 3 protons in that nucleus. The first shell, let me draw it over here. For some reason, it cuts me off right there. So I got 3 protons here. I got my first shell. And that can hold 2 electrons. So I'm going to have 2 electrons in that. There's 1, there's 2. Remember, I got 3 electrons, so I got 1 left. Where am I going to put it? I'm going to put it in the second shell. Second shell. It can hold 8, but we only have 1 left. Right? We put 2 in the first shell, 1 in the last shell, in the second shell. So that's 3 electrons. So in n equals 1, we can say, okay, there's 2 electrons that are living in that shell. They're orbiting in that area. And then in the second energy level, n equals 2, there's 1 electron. So a total of 3. 2 electrons in the first shell, 1 electron in the second shell. You have to fill the inner shell first. Okay, so as you build an atom, you have to put electrons in that first shell until you reach 2. And then you go to the second shell, excuse me, and you can put up to 8 electrons in that second shell. And then you have to go to the third shell, and you can put 8 in it, and so on. And it continues. So let's try beryllium. Beryllium. Oh, let me write the Lewis dot structure for lithium. Lithium would be Li for the symbol, and it's going to have 3 electrons buzzing around it. All right, here's beryllium, 4 protons, 4 electrons, and I promise we're almost done. Here's my nucleus, 4 protons. Just this dot is my nucleus. Here's the first shell. The first shell can hold up to 2. I'm going to put an electron there. I'm going to put an electron there, and they're zipping. Can I go back? I can't go back. Okay. So I got 2 electrons in that first shell. I got 4 total, so I got 2 more. So I'm going to do my second shell, and I can put 2 electrons in it. So n equals 1. I'm going to say, okay, 2 electrons. N equals 2. 2 electrons, total of 4 electrons. All right, now let's skip ahead. Let's do sodium. Sodium is element number 11, so it has 11 protons. And this is the last one, 11 electrons. So I'm going to have my nucleus here. 11 protons in that nucleus. All right, then I have my first shell. I'm going to have 2 electrons in there. There's an electron, there's an electron. I had 11, I took out 2. I got 9 electrons to go. So second shell can hold 8. So I'm going to put 8 electrons in that second shell. Okay. I'm going to subtract that from what we had. Now we have 1 electron left. Where's it going to go? Where's it going to go? Third shell. Oh, that's terrible. We could do better. Third shell. Woo! Oh, it's not much better, but okay. Third shell, 1 electron. So in summary, n equals 1, 2 electrons. N equals 2, second shell, 8 electrons. N equals 3, 1 electron. So that means there's 2 electrons in the first shell, buzzing, bzz, and they have a certain energy, and that energy is different than the other shells. It's much greater energy the further you go out. All right, so the atom almost gets unstable as it gets more and more electrons, right? So 2 electrons in the first shell, 2 electrons in the second, or 8 electrons in the second shell, and 1 electron in the third shell. So let's draw the Lewis dot structure for sodium. 11 electrons. Actually, it's got 11 electrons, right? There's 11 total, 11 protons, 11 electrons. But when we write the Lewis dot diagram for the atom, we are only going to look at the outermost shell. What is the outermost shell here? It is the third shell. How many electrons are in it? 1. And so I'm only going to put 1 electron there. Okay. All right, now let's practice the Lewis dot diagram structure again. So hydrogen, 1 electron. Helium, 2 electrons. Lithium, 3 electrons. Beryllium, 4 electrons. What's next? Boron, 5. The boron? 5, yeah, boron. 1, 2, 3, 4, 5. And then I kind of pair up the electrons when I run out of space. So those are going to be paired. What's next? Carbon, 1, 2, 3, 4, 5, 6. So notice it's got 2 pairs. Nitrogen, 1, 2, 3, 4, 5, 6, 7. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Now oxygen is full. That's as much as you can get. Okay, so what's our next element? And actually oxygen would have 8 protons, 8 electrons, and so 2 would be in the first shell. That'd leave us 6, and so technically it would be 6 left over. So I should erase 2 here. because remember when we draw these pictures, we only want to show the outermost electrons. So this would have 6, this would have 5. 1, 2, 3, 4, 5. This would have 4. This would have 1, 2, 3, 4, 5. We'd have to erase 2, so I would only have 3. 1, 2. This would have 2. So I'm messing these up. There we go. So we're only going to be showing the electrons that are on the outermost shell. Okay. But I'm just showing you another way that we can represent the electron structure. We can write the symbol for the element and draw a number of dots. The number of dots tells us how many electrons are in the outermost shell. Okay. All right, so make sure you guys do the exit ticket and have a great one.